फ्रेंड्स, इस वीडियो में हम ऑप्टो इलेक्ट्रॉनिक जंक्शन डिवाइसेस के बारे में डिस्कस कर रहे हैं। चलिए शुरू करते हैं आज की अपनी ये वीडियो।
Optoelectronic junction devices are PN junction devices which work because of the current carriers that are generated by photons. Photodiodes, light-emitting diodes, which are referred to as LEDs in short, and solar cells are examples of optoelectronic devices. A photodiode is a device that is used to detect optical signals. It is a photodiode in your TV set that allows you to operate your TV using a remote. A photodiode is a specially fabricated PN junction diode with a transparent window that allows light to be incident on the diode. We know that light consists of tiny bundles of energy called photons, whose energy in turn depends on the frequency of the light. We also know that electrons in the semiconductor atoms of a diode need to overcome an energy gap to become free and create electron-hole pairs that act as charge carriers in the diode. When photons of light with energy greater than the energy gap fall on the diode, the photons get absorbed by the semiconductor atoms, leading to the creation of electron-hole pairs in the diode. A photodiode is designed so that the maximum number of electron-hole pairs is created in the depletion region around the PN junction. We know that the depletion region has an electric field created due to the separation of static charges on both sides of the PN junction. As soon as an electron-hole pair is created, the electric field across the depletion region pushes the hole towards the P side and the electron towards the N side. Due to this movement of charge carriers, a small photocurrent is generated through an external load connected across a photodiode. The magnitude of the photocurrent increases with an increase in the intensity of the incident light. However, this change is too small to be measured in the absence of any external bias. The magnitude of the photocurrent is too small compared to the large current that flows through the diode under forward bias. Thus, the change in photocurrent with change in the intensity of light is very difficult to measure when a diode is operated under forward bias. However, the change in the magnitude of the photocurrent with the intensity of the incident light can be measured when a small current flows through the diode under reverse bias. Thus, a photodiode is always operated under reverse bias. The IV characteristics of a reverse biased photodiode for different intensities of incident light are shown here. A light-emitting diode, or an LED, is a device that produces photons of different frequencies of light. An LED is a specially fabricated, heavily doped PN junction diode encased in a transparent cover which allows the emitted light to shine through. An LED is operated under forward bias, which increases the diffusion of minority charge carriers across the PN junction. This leads to the recombination of the electron-hole pairs, which results in the liberation of energy in the form of photons. The energy of the emitted photons and the color of the light produced depends on the nature and the band gap of the semiconductor material used in the LED. Here is a list of some semiconductor materials used in LEDs of different colors. LEDs offer several advantages listed here over conventional electrical light sources. Low operational voltage and power consumption. Instant on-off switching without any warm-up time. Source of near monochromatic light. Long life and negligible wear and tear. LEDs have low reverse bias breakdown voltages. Thus, care must be taken that they do not get connected in reverse bias across a high voltage source. Now let us consider a solar cell. A solar cell is a device that converts light energy into electrical energy. The solar panels that you see connected to solar power appliances are made of a large number of individual solar cells. A solar cell consists of a thin, flat wafer of P-type semiconductor, on which a very thin layer of N-type semiconductor is grown to create a PN junction with a large surface area. The back of the P side is coated with a metal to form a metallic back contact. The top of the N side is provided with a metallic grid contact that covers only a small percentage of the total exposed area of the cell. A solar cell works when light is incident on it from the top over the N side of the device. A solar cell works on the same principle as that of a photodiode, where incident light generates electron-hole pairs in the depletion region of the PN junction. As in a photodiode, the holes are pushed towards the P side and electrons are pushed towards the N side due to the electric field in the depletion region of the solar cell. The holes pushed towards the P side are collected by the back contact, while the electrons pushed towards the N side are collected by the grid contact. This collection of charges makes the back contact positive and the grid contact negative, and gives rise to a current when a load is connected between the two. Unlike a photodiode, a solar cell works without any external bias. The large surface area of the PN junction in a solar cell generates measurable photocurrent, making it a source of electricity. However, just like a photodiode, the photocurrent produced by a solar cell depends on the intensity of the incident light. If we plot the intensity of solar radiation against its energy, we find that the maximum intensity radiation is produced by photons having energy equivalent to 1.5 electron volts. Thus, semiconductors having band gaps lower than 1.5 electron volts are used in the manufacturing of solar cells. Here are a few examples. In semiconductors having band gaps higher than 1.5 electron volts, only a small portion of the total solar radiation is used to produce photocurrent. Thus, such materials are not preferred in the making of the solar cells. In semiconductors having band gaps much lower than 1.5 electron volts, most of the incident radiation is absorbed by the top layer of the cell. Thus, very little radiation reaches the depletion region to produce electron-hole pairs that gives rise to the photocurrent. Hence, such materials are also not preferred in the making of the solar cells. Besides band gap, the other criteria for selection of suitable material for solar cells include high solar radiation absorption capability, good electrical conductivity, and ease of availability and cost. Here, we can see the IV characteristic of a solar cell, which is drawn in the fourth quadrant, as it does not require any external bias and acts as a source of electricity.
दोस्तों, यदि आज की वीडियो आपको अच्छी लगी हो तो लाइक कीजिए, चैनल को सब्सक्राइब कीजिए और अपने दोस्तों के पास इस वीडियो को शेयर कीजिए। अगर आपका कोई कमेंट हो तो कमेंट बॉक्स में नीचे जरूर लिखिए। थैंक यू।